So as it relates to the equations for the energy in simple harmonic motion, so we already described the fact that at the amplitude, right, we are at max potential energy because velocity is 0 at the amplitude, and at the equilibrium point where x is 0, v velocity is at its maximum. Therefore, when we're at equilibrium now, the kinetic energy is at its maximum. We described this already, right? Now, the potential energy of this system is going to be described as half times the spring constant, K, right? That we'll look at for springs here, right? That constant K, if it is not the spring, it would just be the mass, right? Times the displacement squared, right? And then here for the kinetic energy now, we have half, right, of that constant K times the amplitude squared minus the displacement squared. So that is the equation here. All right. And then we can also figure out what comes from the graph here as well. If the x is 0, if displacement is 0, then kinetic energy would be equal to half k times the amplitude squared, right? Well, if the potential energy of x is 0, then 0 is going to occur there, right? Hopefully you guys see that. Can you guys see that? We're saying when we pass the equilibrium point, we end up with a huge kinetic energy. So if x is 0, then we get a larger value for the kinetic energy. But if x is 0 for the potential energy, then that is 0, right? If x is the maximum, no, if x is a, then potential is going to be 0, but kinetic energy is going to be, well, sorry, potential is going to be maximum, but kinetic energy is going to be 0. Can you guys see that without me writing, or you would like me to write that? So we can mathematically describe the values of the simulation we just saw, you know. You guys would like me to write it or no? No? You don't need to write it. Okay. So just saying that when x is equal to 0 here, then we have max kinetic energy, Ke max. And it's when x is 0, right? And then for Pe max now, it's when x is equal to the amplitude, or we have x max. All right. So forced oscillations and resonance, we are out of the math, guys. The math is done, right? So forced oscillations, when a system is driven by an external periodic force, it undergoes forced oscillations. The amplitude of these oscillations depend on the relationship between the driving frequency and the system's natural frequency. We're going to speak about these things. They're very important. We also have something called resonance. I know that a number of persons here know when I speak about resonance, I speak about the movement of electrons, right? But in physics, what we're speaking about is driving frequencies matching the natural frequency of a system, right? So at the resonance, the amplitude of oscillations become maximal due to the constructive interference of energy supplied by external force. I'm going to be speaking about some of these concepts later, all right? So this is the amplitude versus frequency, a resonance curve. This is what we call a resonance curve, right? So amplitude of force vibration is going to be on our y-axis, and on our x-axis is going to be the frequency of the force vibration, right? And at two specific points, we're going to be able to recognize the resonance frequency and the natural frequency of the body. We're going to be describing damping as well, low damping versus high damping and critical damping. These are concepts that the syllabus calls for us to understand. So as the frequency of a driving force approaches the system's natural frequency, the amplitude increases. So as we can see, as we approach natural frequency, the amplitude of the wave increases. Right? So we're approaching this natural frequency right here, and the amplitude will start to increase towards that natural frequency. Right? Peaking actually at the resonance frequency. We're gonna see how this works, right? So examples of force vibrations. When we play musical instruments, we're forcing, for example, the strings on a guitar to vibrate. And as you can see on this GIF here, it vibrates on a transverse wave and it is sinusoidal, right? X is going to be equal to A sine omega t, right? So the guitar strings will vibrate at its natural frequency when sound waves or matching frequencies strike the string, right? Of the matching frequency strike the string, resonance amplifies the sound, right? So when we actually cause these strings to vibrate, right, we're resonating it, we're causing some forced oscillation of the spring, and when the sound waves, right, now matches the frequency, that sound is amplified for you to hear the sound of the guitar, right? So us disturbing the spring causes the movement of particles, which turns into sound waves. Fine so far? Are we okay with this example so far of force resonance? Okay. Examples of other force resonances: swinging bridges, right? So, for example, the Tacoma Narrows Bridge disaster, right? Hopefully we're able to see this video. I could send you guys a link. I want you guys to watch this video specifically, right? So with the disaster itself, what happened is that the bridge here, so we can see that the bridge is actually swaying here, and this is due to the wind, right? So the wind would actually cause the bridge to actually sway like this. So just going back to the part in the video that we can see the swaying with the car on it and the bridge moving from side to side. What is happening is that the wind applies such force to the bridge that it actually oscillates the bridge, and then that wind now starts to match the bridge's natural frequency, causing that oscillation, and eventually the bridge would collapse, right? So it causes a catastrophic resonance for the bridge to sway side to side. So while we're studying these things and we're talking about amplitude and this and that, right? These things are applied, right, especially through civil engineering for the persons who want to become engineers as it relates to these things. This integrity and structure of buildings, right? We have to look at their natural frequency, we have to look at their resonance and the oscillations, right? And look at what amplitude will be achieved and whether or not we're going to be anything like breeze or even earthquake, right, can allow for that system to reach a catastrophic resonance. If so, the structure will collapse, right? So we're looking at things like that for forced resonance, right? Another example of forced resonance would be the standing wave in a microwave. It is we who cause, right, the apparatus to emit these microwaves. So microwaves will drive water molecules at their resonant frequency to now heat the food effectively. For those who are Total Chemistry Unit 2, we know that the infrared or the microwave frequency will cause molecules to vibrate, and this vibration is when the molecules have reached their resonance frequency, right? So microwaves are examples of forced resonance, right? It forces, right, a wave to be emitted and it resonates in this way that you can see in the GIF here, right? And it causes other molecules, for example, water molecules in your food, to resonate. When particles start to move and vibrate, they have more kinetic energy linked to heat through friction, and it is through this microwaves cause food to heat, right? So hopefully I'm bringing across the concepts of the oscillations of these waves and how they're actually applied in real life scenarios. So we looked at the musical instruments through, for example, the guitar, right? Resonance is important in understanding resonance and oscillations, and simple harmonic motion can allow us to gain knowledge of how we can actually mitigate disasters of buildings and structures reaching their natural frequency, right? And that's how we construct buildings in a way to actually not approach, well, for example, when buildings are in earthquakes, right, we try to build them in such stable structures so they don't actually approach their natural frequency and then actually knock down, right? So that's how buildings actually get destroyed through earthquakes, because a P wave in an earthquake, which is seismic, it causes oscillations of the earth forward and backwards, and it causes the buildings to reach their natural frequency and start to resonate it violently. And that's what happens there, right? So understand and not having an understanding of simple harmonic motion can allow us to mediate those issues, as well as in the microwave example here, allow us to create devices. For example, MRIs are another example of how we can use waves to our advantage, right? We're just looking at something like that. That should really be simple, right? So resonance in high rise or buildings and earthquakes as well is something very important that we can look at, right? So earthquakes are caused by different types of waves, different types of P waves, right? And we have different structures, right, that actually prevent these types of oscillation. So we dampen the oscillation, we slow down the oscillation so that the building does not reach a destructive or a catastrophic resonance, right? So we use tune mass dampers, right, or base isolators, right? Those are used, right, in the systems, well, to alter the system's natural frequency and to dissipate energy, right? So we don't want the waves to create so much energy the building can be toppled over. So we try to dissipate that energy either using isolators being dug into the ground, right, or creating tune mass dampers that are placed on high-rise building and skyscrapers, right? So these things are important. Understanding waves and simple harmonic motion is important in preparing structures for civil engineers. All right. So those are the examples that we're looking at. So cases of resonance, desirable and undesirable. So we have desirable resonance. So for example, we willingly cause resonance, right, and oscillatory motions when actually using musical instruments, because it's through those oscillations we get the sound efficiently, right? Radio tuners and stuff like that. So frequencies, signals, right? So the way how I'm speaking here and you're able to hear me, these signals, right? Radio signals, Wi-Fi, regular radios, TVs, right? They use different types of signals. We generate the waves, right? And those waves are going to be used to transport information. MRI machines, as I mentioned before, utilize resonance in atomic nuclei to produce detailed imaging, right? So what we do, we actually vibrate the nuclei of the atoms, right? And that can be picked up by the machine so we can detect different types of tissue in the body, right? That's a part of medical physics, right? Undesirable cases now in bridges, machinery, and earthquakes, right? When we have uncontrolled vibrations that may lead to that catastrophic damage or structural failure. All right. So we have that there. So those are the causes of resonance, desirable versus undesirable. All right. And then we have something called damping. All right. So damping refers to gradual reduction in the amplitude of oscillations. So we're trying to reduce the amplitude of oscillations and we're trying to dissipate the energy as either heat, sound, or mechanical friction. So we have an oscillation and we're trying to stop the oscillation, right? Or we can increase the oscillation. We have four types of damping, right? We have under damping, critically damping, over damping, right? Well, three types, my bad, right? We have three types of damping, right? So under damping, right, oscillations will continue but gradually decrease in their amplitude, right? So we're looking at under damping, right? So the blue line is under damping. So we can realize how, let me use the pointer, how we start with the amplitude will continue but it will gradually decrease until the oscillation is complete, right? For critically damped systems, they return to equilibrium in the shortest amount of time. So that green dotted line, shortest amount of time will return to equilibrium. And for over damping now, right, the system returns to equilibrium without oscillating, but it's more slower, or it happens more slowly, right, than critically damping, right? So let me just repeat. For the underdamping, right, the system continues to oscillate but gradually reaches equilibrium. For overdamping, the system does not oscillate but reaches equilibrium in its own timing. But for critically damping, it tries to reach equilibrium in the shortest amount of time possible. Now, how is this important at all? How is this important at all? We can look at the actual effects or the actual uses of damping, right? For example, in motor vehicle suspension, right? We use these types of damping, right, as shock absorbers, right? So we actually have this. So the type of damping being used here, I want you guys to figure out, right, the type of damping used in each of these situations. But we use simple harmonic dampening, right, to actually absorb shock from the cars. So when the cars go through, for example, potholes or going over a rocky area and stuff like that, we don't want the car to start to vibrate until until the car starts to become destroyed. These suspensions, right, and shock absorbers will actually take the oscillations caused by the rocky terrain or potholes or whatever, right, and now stop the lower the amplitude or stop the oscillations and bring it to equilibrium, right? So that's what happens, right? We have an oscillation or vibration, and the shocks or the vehicle suspension will now try to reduce that oscillation as much as possible and to make sure that the car maintains, right, contact to the road, and it allows for better handling in motor vehicles. All right, so that's one use of dampening, right? We also have damping over here. We have over damping here in analog electrical meters. For example, when we're using our multimeter or using our ammeter or voltmeter, right, the pin, the needle, right, uses damping, right? So to stop the needle quickly after it moves to indicate a value, for example, if the needle moves to 20 and then continues to oscillate, we won't be able to read, right? Okay, and suspension bridges for that, for the slide before, right? But yeah, so we also have this damping here for the meters, right? For example, if we move the value we're trying to determine how many amperes, right? We don't want the pin to continually oscillate. We want it to stop exactly on a value. So we use damping there as well. Electromagnetic damping we can use. We can use a magnetic field to slow the oscillation of the pin for it to directly point in a value that we need. So that is an example there. Also door closures, right? So the hydraulic dampeners, right? Dampers that we use for door closures. So for example, for some doors that have these on, right? When you swing a door, it will immediately come to a slow movement to shutting. So it doesn't allow the door to swing loosely, right? But it dampens the oscillation and the resonance of the door and allows it to move slowly to closing, right? So this is an example of using hydraulic or air dampeners, right? So it prevents any type of noise or damage to the door frame, all right? So it ensures safety as well and reducing risk of injury of swinging doors or anything like that, right? So we try to reduce the oscillation of these objects, right? And that's what damping really is all about. Okay? And that brings us to the end of simple harmonic motion. That is it.